So I think we could get started. I think we could get started now. Hi, everyone. My name is Leah Yamashita, and I'm the manager of the Freight Policy section here at CARB. I'd like to welcome you to today's public workshop to discuss the draft 2025 Cargo Handling Equipment Technology Assessment. Before we get started, I just want to thank you all for joining us today. And I'd also like to thank those of you who hosted us for site visits, met with us, or provided information. Your input is important to us, and we very much appreciate your time. And with that, I'll turn it over to Joelle to get started.
Thanks, Leah. I'm Joelle Howe, a staff air pollution specialist at CARB and the cargo handling equipment team lead. For those of us on Zoom, if you'd like to make a comment or ask a question during the discussion, please use the raise hand feature to be added to the speaking queue. You can also submit questions at any time by using the Zoom Q&A box. If you're calling in by phone, press *9 to raise your hand, and we will unmute you when it is your turn to speak. Next slide. Please take a moment to check that your screen name shows your full name and organization if you haven't done that already. Use the format first name, last name, -affiliation, like my name, Joelle Howe -CARB. You can do this by clicking the 3 dots on the video next to your name in the participant list and then selecting Rename. This helps us keep track of who's here and makes follow-up easier. Next slide. A couple more quick reminders. If you need technical help, please use the Q&A function to request assistance. Our meeting materials for today are available on the Cargo Handling Equipment Technology Assessment webpage. We'll drop the link in the chat for easy access. And finally, we are recording today's meeting, and it will be posted on the same webpage after the workshop. Next slide. Here's a quick overview of what we'll be covering today. We will start with some background on cargo handling equipment. You'll hear me refer to this as CHE from time to time. Then we'll introduce the draft CHE technology assessment and walk through our approach. From there, we'll dive into the results of the technology assessment, what we found in terms of technology, infrastructure, and costs. We'll conclude with some key takeaways and point you to the appendices if you want to dig deeper. And finally, we'll open the floor for your questions and input throughout today's presentation. Next slide. Before we get into the assessment, I'm going to start with some background information. Next slide. When we talk about CHE, we are using the definition from our current regulation. In plain terms, CHE is off-road, self-propelled equipment that is used at a seaport or intermodal rail yard, and those are what we'll call facilities today. It is used to lift or move cargo, whether that's containers, bulk, or liquid, or to carry out routine maintenance and repair work. As you know, this covers a pretty wide range of equipment, from yard trucks and cranes to utility trucks and aerial lifts. Next slide. The Mobile Cargo Handling Equipment Regulation, which CARB adopted in 2005 and amended in 2011, has significantly reduced emissions from diesel-powered CHE. It requires engines to meet particulate matter, or PM, and NOx limits. And this has driven real progress, especially as older engines must be replaced with cleaner models. The regulation has been effective, but it was not designed with zero-emission equipment in mind. So where does this leave us today? Next slide. Let's dig into the emissions profile of the sector. Based on CARB's 2022 CHE emissions inventory, today there are over 5,000 pieces of cargo handling equipment operating at seaports and intermodal rail yards across the state. The largest concentrations of those are at the ports of Long Beach, Los Angeles, and Oakland. And most of this equipment across the state is still diesel powered. And the number of CHE is expected to double by 2050, which makes understanding the sector and planning for its future even more important. Next slide. This graph shows projected statewide PM 2.5 and NOx emissions from CHE through 2050. Thanks to the current regulation and natural turnover, emissions are expected to decline for the next decade. But without zero-emission equipment, progress stalls. Emissions eventually level off even with full compliance. And that is the key takeaway. We've made real progress, but we're approaching a plateau, and this is where the opportunity lies to go further. Next slide. Okay, now let's move on to the draft technology assessment. As we've already covered on the agenda slide, today's discussion will cover these 4 aspects of the technology assessment. Next slide. I will start by explaining our purpose of the assessment, how and why we developed it, and how it supports our broader goals at CARB. After that, we will walk you through our approach, findings, and what we learned about the current state of zero-emission technologies. Next slide. At CARB, our mission is to protect public health and fight climate change. And cutting freight emissions is a big part of that work. The technology assessment supports this mission by helping California reach its multiple risk reduction and air quality goals. It also supports the Governor's Executive Orders, or EOs, which call for zero-emission off-road vehicles and equipment by 2035 where feasible. The assessment evaluates the readiness of zero-emission technologies for CHE, what's on the market now, what's in development, and how do these technologies perform in real-world settings. This document is an update to our last CHE technology assessment published in 2015. It also supports planning and regulatory actions such as the Mobile Source Strategy, State Implementation Plan, Scoping Plan, and funding plans for clean transportation incentives. Now I'll turn it over to Jeff, who will walk us through the details of the assessment.
Thanks, Joelle. Hello, I'm Jeff Jacobs. I'm an Air Resources Engineer in the Freight Policy section at the California Air Resources Board and the lead staff for the technology assessment. Here we have the key elements we evaluated for each zero-emission technology in the assessment. For each zero-emission technology, the following elements are discussed: technology description, technology readiness, emissions benefits, infrastructure requirements and considerations, economics, technology outlook. Next slide, please. To develop the assessment, staff conducted extensive research, including visiting seaports and intermodal rail yards, meeting and corresponding with CHE manufacturers, operators, mechanics, and facility operation managers, reviewing technology assessments such as those from the Port of Long Beach, the Port of Los Angeles, and the Port of Oakland, reviewing news articles, journals, and CHE demonstration reports, conducting technical research. The assessment is based on data available through January 2025. So demonstrations or other events that affect CHE developments or costs that have occurred since then are not included in the assessment. Next slide, please. The assessment separates 25 of the most common types of CHE into 3 categories. The 3 categories are bulk material CHE, container CHE, facility support CHE. These categories are simply for our purposes of organizing the assessment. For the most part, each type of CHE fits clearly into one of these three categories, except for forklifts and some cranes, which can be used for all three purposes. I'll pause for a moment so you can see the different types of CHE that are in each category. If you have any questions about the list, we will pause for questions in a moment. Next slide, please. Here are some examples of the types of CHE. Bulk material handling CHE is equipment that is commonly used in the construction industry. It is used to move bulk cargo, which can include dry bulk cargo like cement, scrap metal, grain, etc., or large bulk cargo like boats, construction equipment, engines, or lumber. Shown here are a dozer, an excavator, a mobile harbor crane, a heavy lift forklift, and a mobile crane. This forklift is a battery electric forklift used at the Port of West Sacramento to move up to 6 1,000-pound bags of rice at a time. And the mobile harbor crane is one of two new grid electric models currently operating at the Port of San Diego. Container CHE. This equipment is used exclusively for moving containerized cargo, which is the majority of cargo. Shown here are a reach stacker, a top pick, a rubber-tired gantry crane, or RTG, and facility support CHE. This CHE is mostly used to support facility operations. It is shared across many different industries ranging from rail to municipal services. Shown here are a sweeper, a rail car mover, and an aerial lift. Next slide, please. For this assessment, staff only looked at zero emissions technologies, those with zero exhaust emissions of any criteria pollutant or precursor pollutant, toxic pollutant, or greenhouse gas under any conditions. This assessment does not include near zero or other advanced technologies that are not considered zero emission. Staff evaluated 3 zero emission CHE technologies: battery electric, grid electric, and hydrogen fuel cell. Note that we use these abbreviations throughout the presentation: ZE for zero emission, BE for battery electric, GE for grid electric, and HFC for hydrogen fuel cell. Next slide, please. This slide is an overview of our approach. There's a lot to unpack here, so I'm going to walk through this process on the left, starting on the left and work to the right. The first panel on the left shows that we evaluated 25 different types of CHE and 3 zero-emission technologies, which produced a total of 75 CHE technology combinations. As you can imagine, assessing 75 combinations could be a daunting task. However, there are many combinations that are not being developed by industry, either because it isn't practical or the technology isn't ready for that type of equipment. So the question arises, how do you evaluate if a combination isn't practical or if the technology isn't ready for that type of equipment? As shown in the second panel from the left, the first step was an initial screen for technology applicability. Technology applicability combines practicality and technological potential. To determine practicality, there were several criteria we used to answer the question, does the technology make functional sense for this type of CHE in 2025? We asked, is there evidence of the technology being used on this type of CHE? If not, is there evidence of the technology being used on similar equipment? If the equipment technology combination meets one of the criteria, it scores 1. If not, it scores 0. Likewise, to determine technological potential, we use several criteria to answer the question, could the technology allow the CHE to meet the duty cycle and operational needs for this CHE within 10 years? We asked, is the CHE technology combination commercially available? Is similar equipment that uses this technology commercially available? If the combination met one of the criteria, it scored a 1. If not, it scored 0. The two scores were then combined, giving either a 0, a 1, or a 2. If the equipment technology combination scored a 1 or a 2, staff continued to assess the equipment. If the combination score was 0, staff did not continue to assess the equipment. 55 CHE technology combinations scored a 1 or 2 and were assessed further. 20 CHE technology combinations scored 0, meaning these CHE technology combinations are unlikely to achieve equivalence to their internal combustion counterparts within 10 years. This takes us to the third panel from the left. The next step was to determine technology readiness. Technology readiness combines commercial availability with operational feasibility. For commercial availability, we used 5 criteria to rate how commercially available the CHE technology combination is. For operational feasibility, we rated the CHE technology combination using 4 criteria, including endurance, performance, reliability, and fueling logistics. The cost of the equipment, the availability of fuel and infrastructure, and the cost of the fuel, either electricity or hydrogen, are considered separately in the assessment and will be discussed in a moment. The scores for commercial availability and operational feasibility were combined to produce a technology readiness score. The score then fell into ranges associated with 4 technology readiness grades, as shown in the 4th panel. Next slide, please. These are the 4 technology readiness grades assigned to the 55 CHE technology combinations. CHE that scored the lowest was given a grade of development, indicating that the CHE is either not being developed at all or still in early development and prototypes are just starting to be tested in controlled environments. This CHE is not ready for deployment. CHE with the next highest score achieved a grade of demonstration, indicating that early models may be commercially available, but the CHE is still being tested and is not ready for full operational deployment. The next technology readiness grade is limited. This grade indicates that the CHE is commercially available and can be deployed, but only in limited operations since it does not yet operate equivalently to diesel-powered CHE. The final technology readiness grade is equivalence. This grade indicates that the CHE has achieved equivalence to its corresponding diesel-powered CHE and is ready for full commercial deployment. Before we move into results portion of our presentation, I'll pause here and open it up for questions and comments on what we've covered so far. Next slide, please. So if you have any questions or comments on what we just covered, you can use the raise your hand feature, submit a question in the Zoom Q&A box, or if you're calling in by phone, press *9 to raise your hand and we'll unmute you. And while we're waiting for questions and comments, we can look at this battery electric top handler.
Jeff, there is a question in the Q&A.
Okay.
Do you want to read it or you want me to read it out?
I got it. Let's see. Did
Okay.
cost, ROI, return on investment, affordability enter into the technology assessment approach? It wasn't included as part of technology readiness, but we assessed those, return on investment and affordability separately. So Tian Boateng will be discussing that in a few minutes, but it's factored, it's kind of combined all together, not for each individual piece of CHE. And hope that answers your question. If not, you can ask it again. Any other questions? Or does anyone on staff have anything to add to that? Okay, I'll take that as a no, and we're good to go on. Oh, let's see. Another question popped in. On slides 9 through 10, are the future emissions calculating the EPA Clean Port projects that will replace dozens of diesel equipment with electric? That is a really good question.
You want me to take that one?
Sure.
No, because the last inventory update took place back in 2022, so it does not.
Great. Good question. Anything else before we move on? Okay, next slide, please. Now that we've covered our approach to assessing the CHE technology combinations, let's talk about the results. This presentation is organized a bit differently than the technology assessment to be as brief as possible, but we will still cover the 6 technology assessment elements that we discussed earlier. For technology readiness, I will go through the technology description and technology readiness. I will then review emissions benefits and considerations for all 3 technologies. Then we'll pause after my presentation to take some more questions and comments. After that, Tian Boteng will discuss infrastructure and economics. And then after that, I will provide our technology outlook for the CHE that we assessed. Next slide, please. Battery electric CHE relies on rechargeable batteries to provide electric power for both movement and cargo handling. The 2 primary battery chemistries are lead acid and lithium ion. Lithium-ion batteries last longer and weigh less than lead-acid batteries, but are more expensive. Because batteries are heavy and expensive, it is challenging to add enough batteries to last the same runtime on a full charge as diesel-powered CHE can operate on a full tank of diesel. So facilities generally want the equipment to operate for either a full shift or even 2 shifts before needing to charge. Alternatively, charging can be done when the equipment is not being used, during breaks, or between shifts. This is called opportunity charging. Next slide, please. The primary benefits of battery electric CHE include increased mobility compared to grid electric CHE, which often requires cables or bus bars for power. Several types of this CHE are commercially available, and battery technology is continually improving with increased capacity, faster charge times, and lower costs. Some challenges with battery electric CHE are that the CHE is more expensive than diesel-powered CHE. The number of batteries is limited due to cost and/or weight constraints requiring more frequent charging than operators are accustomed to. It takes longer to charge battery electric CHE than refueling equivalent diesel-powered CHE. And charging infrastructure occupies real estate that could otherwise be used for cargo operations. Next slide, please. Here's a summary of the commercially available battery electric bulk material CHE and their technology readiness grades. Note that commercially available CHE are offered by the manufacturer through standard channels like distributors or dealers. Non-commercial units are prototypes or special builds that are not produced at quantity or offered through standard distribution channels. I'm going to pause here to give a chance to look at the data. The item that stands out the most on this slide is the 39 commercially available models of battery electric heavy lift forklifts. Several of these models are eligible for funding through CARB's Core Voucher Incentive Program. Another standout data point is that there are no battery electric log stackers either commercially available or in development. In fact, log stackers are the only CHE for which there are no zero emission models using any of the 3 technologies, either currently commercially available or in development. Next slide, please. This slide provides a summary of the commercially available battery electric container CHE and their technology readiness grades. I'm going to pause here to give a chance to look at the data. There are a few noteworthy items here. First, AGVs not only achieve a technology readiness grade of equivalence, but 100% of this CHE in California is zero emission, representing 100 pieces of clean CHE operating at the Port of Long Beach. Second, both top handlers and yard trucks receive a technology readiness grade of limited due to both second and third generation models becoming available, and there are models that can operate for 2 full-hour shifts before needing to recharge. Next slide, please. While there are many models of battery electric facility support CHE, we do not have any information on their performance at seaports and intermodal rail yards, which is the primary reason for the technology readiness grade of demonstration. We are aware of a couple electric railcar movers operating at seaports in California. So if you have information on their performance, please share. I'll give a few more seconds to review the table. Next slide, please. Grid electric technology for CHE involves a continuous connection to the utility grid using cables, bus bars, or pantographs. Grid electricity is practical for CHE that is mostly stationary or follows predictable paths, such as ship-to-shore cranes, rail-mounted gantry cranes, or rubber-tired gantry cranes. Most grid electric CHE still need batteries, but less than is needed for battery electric. Providing a grid connection for moving equipment is challenging and often requires significant infrastructure changes, which in turn require a lot of planning. Dynamic charging from the grid is being investigated for on and off-road vehicles, but is not yet used for CHE. Next slide, please. Some of the benefits of grid electricity for CHE include constant power, which can reduce or eliminate the need for batteries. It can reduce or most likely eliminate the need to charge. Nearly all new ship-to-shore cranes and rail-mounted gantry cranes are grid electric. New wireless dynamic charging technologies for mobile equipment are being developed, and some dynamic wireless charging CHE will soon be tested. Some of the challenges with grid electricity for CHE include limited mobility, and infrastructure for grid electric CHE can be disruptive during installation, and once installed, it can take up real estate that was used for operations or storage. Next slide, please. This table shows commercially available grid electric bulk material CHE along with corresponding technology readiness grades. I'm going to pause here for a chance to look at the data. Only 4 types of grid electric bulk material CHE made it through the initial technology applicability screening, since the technology isn't very practical for most CHE as it requires a constant physical connection to the grid. However, cranes and excavators lend themselves well to grid electric connections using a cable, since the unit can remain stationary while the cab, boom, and arm can rotate and articulate to move material. Next slide, please. This table shows commercially available grid electric container CHE along with the corresponding technology readiness grade. I'm going to pause here to give a chance to look at the data. The most notable items from this table are that rail-mounted gantry cranes and ship-to-shore cranes achieve a technology readiness grade of equivalence. In fact, grid electric is the industry standard offering for these 2 types of CHE. I'll mention here that while putting together the assessment, there have been a couple of announcements regarding future demonstrations of dynamic wireless charging for yard trucks. However, as of January 2025, which was our cutoff for data collection, the demonstrations had not been launched. Next slide, please. There were no commercially available models of grid electric facility support CHE. All grid electric facility support CHE achieve a technology applicability score of 0. This is mainly because of no current development of grid electric versions and the commercial availability of battery electric versions. battery electric, and fuel cell solutions are commercially available and provide zero emission solutions for this category of CHE. Next slide, please. Hydrogen fuel cell CHE uses a fuel cell instead of a battery or connection to the grid to operate. A hydrogen fuel cell is similar to a battery but uses hydrogen as a fuel instead of needing to be recharged. There are many different fuel cell technologies, but polymer electrolyte membrane, or PEM, fuel cells using hydrogen as the fuel are the most common for commercial vehicles, including CHE. Hydrogen fuel cells are a mature technology, but not currently used in many CHE. Next slide, please. Some of the benefits of using hydrogen fuel cells for CHE include the same freedom of mobility as batteries, comparable refueling times for hydrogen fuel cell CHE as with diesel-powered CHE, reduced battery dependency. Some of the challenges associated with hydrogen fuel cells for CHE include limited commercial availability of hydrogen fuel cell CHE. Hydrogen CHE is more expensive than diesel CHE. Hydrogen supply and support infrastructure are not readily available. Hydrogen as a fuel is more expensive than diesel per unit of energy. Next slide, please. This slide provides a summary of the commercial availability of hydrogen fuel cell CHE, as well as the technology readiness grades. I'll pause here for a moment to give a chance to look at the data. A few noteworthy items from this table are that other than heavy lift forklifts, there just aren't many commercially available models for bulk material CHE. Most are still in the development phase. Bulk material hydrogen fuel cell CHE is being demonstrated globally, indicating that there is market interest. However, most of these demonstrations do not occur at seaports or intermodal rail yards, so there's very little information about operational characteristics. Next slide, please. This table shows commercially available hydrogen fuel cell container CHE along with the corresponding technology readiness grade. I'll pause here to give a chance to look at the data. There were no commercially available models of fuel cell container CHE. Because of the demonstrations of the RTG at Houston Terminal at the Port of Los Angeles and the ZCAP demonstration of a fuel cell yard truck at the TraPac Terminal at the Port of Los Angeles, we've been able to assess these two CHE, and they achieve a technology readiness grade of demonstration. As a side note, since our January cutoff, one fuel cell yard truck has become commercially available. Next slide, please. This table shows commercially available hydrogen fuel cell facility support CHE, along with the corresponding technology readiness grade. I'll pause here for a moment to give a chance to review the data. Some of the highlights on this slide are that there are commercially available models of hydrogen fuel cell aerial lifts and sweepers. Hydrogen fuel cell sweepers have made a lot of progress and achieve a technology readiness grade of limited. It is not likely that there will be significant development of hydrogen fuel cell cone vehicles and railcar movers within the next 10 years due to extensive lead times for product development. But there are 4 manufacturers of medium and heavy duty trucks that have announced plans for general purpose cabin chassis trucks that are suitable for facility support CHE. Next slide, please. Zero emission technology has each zero emission technology has a section describing emissions benefits and considerations. This slide sums up the information from all 3 technologies into one table. The most important benefit is that all three technologies have zero exhaust emissions. For both battery and grid electric CHE, California's electricity comes from nearly 60% renewable sources and is continually getting cleaner, providing a clean source of power. Using grid electric and hydrogen fuel cell CHE can reduce e-waste caused by spent batteries, help avoid charger congestion and unmanaged charging, which we will talk about more in a minute, which in turn helps alleviate stress on the grid. This may help reduce dependence on peaker plants, which are power plants used during peak hours when the regular power generation sources are being stressed. Peaker plants often do not use renewable power generation sources. Hydrogen can be produced renewably, and hydrogen fuel cell CHE that use hydrogen from renewable sources have the best life cycle emissions profile. However, because hydrogen is such a small molecule, hydrogen leakage is a challenge and has indirect greenhouse gas effects. Next slide, please. Before we move on to the infrastructure and economics portion of our presentation, I'll pause here and open it up for questions and comments about what we've covered so far. As a reminder, if you'd like to ask a question, you can use the raise hand feature. You can submit your question by using the Zoom Q&A box, or if you're calling in by phone, press *9 to raise your hand and we'll unmute you. And while waiting for questions and comments, we can look at this battery electric yard truck that is currently in operation.
But Jeff, we have about 4 questions in the Q&A right now.
Okay.
If you want to just go down the list, that's I think that's probably best.
I'll open that up. The CEC has
grant funding opportunity
on the street that requires 3 CHE to charge at each charge point, yet this assessment indicates that battery electric is currently a challenge for even just 2-shift operations. Does ARB envision any practical possibility that CHE at ports could realistically assign 3 units to a single charger and allow 3 units of full operation? So this is primarily an infrastructure question. And we'll talk about infrastructure right after we're done with our Q&A right now. We acknowledge that there is this challenge of charging infrastructure. The question, does ARB envision any practical possibility about assigning? So we don't specifically have recommendations on how the ports should charge their equipment. We do talk, and like I said, in a moment, we'll talk more about the infrastructure and the implications of that, but we do not go into detail about how that charging will happen. So, but yeah, we'll address that more, and we'll see if we answer this question in more detail. If not, you can circle back and ask if we don't address your comment. Next one is reduced frequency of maintenance for battery electric. Oh,
sorry, Jeff.
That's okay. Is reduced frequency of maintenance for battery electric not included as a benefit on slide 24 because it hasn't really been proven to be so? Reduced frequency of maintenance for battery electric. Okay, so we'd have to go back to, I'm assuming slide 24 is the table showing the okay. Oh, okay. Reduced frequency of maintenance. So that one of the benefits of the battery electric equipment is reduced maintenance. However, unfortunately, because of the newness of the equipment, that hasn't been realized for most of the demonstrations that have occurred. typically what'll happen is like one part might have to wait, and it kind of holds things up. So unfortunately, the supply chains haven't been in place to realize the potential reduced frequency of maintenance. So that is included in the when we do the analyses of the demonstrations, but that reduced frequency of maintenance has not yet fully been realized, but it is one benefit that we do expect to see. So that's a good point, and we'll consider adding that. Next one. All right. In the tables that assign technology readiness grades, showing the 3 zeros and then labeling it development implies that these are actually in development. Is that the case? So development is basically from 0 to I forget what the exact scoring is, but it starts at 0, which basically says that it's not. it allows for the case of not yet being in development. So even though it says development, it just means, you know, there isn't anything on the market. There's nothing being demonstrated. So yes, it can actually a score of 0 can technically mean that it is not in development, but that's the score that it gets. Unfortunately, if often there's a lot going on behind the scenes that we're not aware of in equipment development, companies don't make it public when they're starting to develop equipment. It's not until we see demonstrations happen where we realize, oh, okay, something is in development. Okay, if not, would it be more accurate to have a 5th designation that does not imply something in development when it is not? That's a fair point. And development is just a title. It's just assigning a value. We can go into if you go into the appendices, you can see the detailed scoring, which, you know, it gives all of the details associated with how we came up with that grading value. Okay, but that's a good point. Next one. With regard to the term development, is there ranking for how long until these equipment types will be available for demonstration and be commercial? No, there is not. Like I said, we a lot of times don't have visibility into what's being developed. And so until there's actually a prototype or an announcement, or, you know, some type of public information, we don't have visibility to how probable it will be that something will come to market. So the answer to that is no. Can CARB help connect technology providers with prospective operator partners? We want to test hybrid hydrogen fuel cell electric powertrains and yard tractors. Testing of this technology has been very limited to date, ZCAP at TradePac. We have minimal points of contact in the container terminal space. What is the best way to reach out to terminal operators? Can CARB help technology provider connect with operator partners? Go ahead, Leah.
That's not typically something that we do, but if you want to follow up offline, we can give you some contact information for some of the trade associations, and you can go from there.
Okay, next. All right. I think this is the next one. Is there any evaluation or assessment of battery degradation over time for the battery electric CHE? That would be a concern for 2-shift operations. That definitely is a good point. And, you know, we did a lot of study on battery degradation as part of our research. However, because there's a lot of information out there, you know, we do reference, you know, we cite various journals and studies on battery degradation over time. However, we don't go into a lot of detail in our assessment about that about that topic, especially since it's changing constantly. And so I would propose to go to the internet and search current research, the current research that's going on for battery degradation. We do address it in our tech assessment, but no, we don't. We do not go into detail. But it is, it is something that is constantly getting updated in industry. So yeah, basically keeping a pulse on what's going on in industry is your best bet. For battery electric CHE, a majority have received a tech applicability score of 2, high potential to perform equivalently to diesel in 10 years. However, there seem to be a number of CHE that have been produced and largely available commercially, yet they are receiving a readiness grade of development or demonstration, or have just received limited. It does not really seem possible for those currently below the limited grade to be equivalent at the 10-year mark. Okay, that's a great point. So what we had to do was look at, like I said, commercial availability. And if a piece of equipment was commercially available, it scored very high for commercial availability, but then we had to combine that with the operational feasibility of where it's at right now, with demonstrations at the ports and intermodal rail yards. And so that's why, like, if there's something that's commercially available and fully functional, but it hasn't been tested out at the ports, that score, that overall technology readiness score, is going to be lower, just because it hasn't been tested out and there aren't very many demonstrations. As far as the outlook for the future, we're going to go more into detail in that in our presentation, but that what we presented so far is just the kind of ability to go head to head with the diesel equipment, the equivalent. And so, yeah, we'll go more into the, kind of future outlook of where this is headed and discuss that in more detail later on in the presentation. All right.
It looks like the top one you still have outstanding.
Okay. Yeah, there's a lag. Sorry, everybody. We're trying to keep up with our technology is trying to keep up with us. If the battery electric CHE is listed as a demonstration technology readiness grade, then why is their number listed as commercially available in the first column? Most of the demonstration equipment from the operator standpoint is a single equipment being tested in the port setting for the first time, with many issues that have yet to be resolved for commercial fleet turnover due to the lack of realistic applications for opportunity charging port operations. Does commercially available equate to equipment fleets that have been deployed in a facility? So, and I alluded to this a little bit previously. So when coming up with our technology readiness grade, it was a combination of commercial availability and operational feasibility. So there, and we pointed this out in the tech assessment, in our technology assessment, that a lot of equipment, there's a lot of equipment out there that is, we look at it as commercially available. It's going through distributors and dealers to be sold on the open market. However, as the question alludes to, that it just hasn't been tested. So that's why it's a combination between, hey, is it available, and how does it operate and function at the ports and intermodal rail yards? And so that combination is what kind of has pulls down the score, the overall grade for most of the technology. So but we do, a lot of equipment is available through our core voucher incentive. There are incentive programs available for the equipment. It just needs to be tested out. And of course, we try to get visibility into the reports that are the demonstrations that go on, and we try to gather that information and include it. But sometimes the information isn't available to us. And so while there may have been demonstrations, we might not have been able to find the information. So I hope that answers that question. If not, feel free to come back. We'll have another Q&A session soon.
I think that's it for now.
Okay, cool. All right, and with that, Tianbo will now discuss infrastructure and economics. Next slide, please.
Good morning, everyone. My name is Tianbo Tan, and I am an air resources engineer at the California Air Resources Board. It's a pleasure to be here with you today. In this portion of the presentation, I'll cover infrastructure requirements and considerations, infrastructure challenges, and economics associated with battery electric, grid electric, and hydrogen fuel cell CHE. First, let's look at battery electric and grid electric infrastructure requirements and considerations. We evaluated the infrastructure required to support electric CHE through three key components. First, we looked at the electricity source, including a statewide grid impact analysis, steps of upgrading utility grid infrastructure, and microgrids. Utility grid infrastructure upgrades can be adding more circuits, modifications of existing substations, or adding new substations, depending on the needs. Second, we looked at charging equipment requirements and considerations. Charging stations, along with components like switchgear, all require space, which is limited at seaports and intermodal rail yards. Permitting and certification processes can influence deployment timelines, which need to be considered when starting infrastructure projects. We also assessed charging station requirements and considerations, including DC, AC charging, and commonly used plug configuration and charging standards. Third, we examined charging logistics. We looked at different charging interfaces, including manual conductive, hands-free conductive, and inductive charging for battery electric CHE. We also examined different charging practices, including managed and unmanaged charging, efficient interfaces like hands-free conductive charging or inductive charging, along with managed charging strategies, can reduce equipment downtime and improve workflow efficiency. The image on the right illustrates how managed charging can reduce peak hour grid demand while continuing to meet equipment charging needs. Grid electric CHE also presents unique infrastructure considerations. Above-ground cable systems can block equipment movement, while underground systems can add expense. Grid electric CHE also face mobility limitations, with RTGs taking up to 45 minutes to move from one stack to another. Next slide, please. As part of our assessment, we conducted a statewide grid analysis to evaluate the additional grid electricity needed at California seaports and intermodal rail yards. This analysis provides a high-level understanding of current grid capacity. Details on assumptions, data sources, and the methodology can be found in Appendix F. Based on our preliminary analysis, we estimate that about 695 megawatts of additional grid capacity would be needed to fully support a zero-emission CHE fleet statewide. Out of the 28 facilities analyzed, 21 currently have sufficient utility-provided load capacity. The remaining 7 will need more load capacity. Even facilities with sufficient capacity may still require infrastructure upgrades, such as installing additional circuits to serve specific locations. Notable shortfalls were seen at the state's busiest ports, the Port of Long Beach, the Port of Los Angeles, and the Port of Oakland. These sites may experience more challenges to full electrification than others. This analysis offers a simplified system-level perspective on grid capacity and is intended to highlight broader trends and potential bottlenecks. This analysis can serve as a useful foundation for more in-depth facility-specific studies in the future. These future efforts will be critical to better understanding and planning for the grid needs required to support widespread adoption of electric CHE at California seaports and intermodal rail yards. Next slide, please. Our assessment identified several challenges to deploy electric infrastructure. High costs remain one of the key challenges for infrastructure projects. Detailed cost information will be discussed in later slides. Next, lengthy timelines for planning and constructing electric infrastructure contribute to delays in infrastructure projects. The permitting process and the need for certification of charging equipment can cause further delays. Space requirements also pose a challenge. Sufficient space must be allocated for electric infrastructure, which can be difficult in already congested seaport and intermodal rail yard environments. Charging equipment issues, such as availability, reliability, and compatibility, can hinder operations. OEMs may take considerable time to address faulty equipment or provide replacement parts for charging systems, resulting in increased downtime for CHE. Lastly, utility grid reliability affects both performance and equipment lifespan. Irregularities in the utility grid, like voltage fluctuations and electrical noise, can negatively affect the lifespan and performance of electric equipment. Next slide, please. For hydrogen fuel cell CHE infrastructure, we focused on 5 key components. First, hydrogen supply. We reviewed current hydrogen production methods, such as steam methane reforming, electrolysis, and biomass-based processes, as well as major projects underway to expand hydrogen production in California. Second, delivery methods. These include gaseous pipelines, high-pressure tube trailers, liquid hydrogen transport, mobile refuelers, and chemical carriers. Each method has distinct costs and considerations. Third, storage methods. We looked at gaseous and liquid hydrogen storage, along with emerging material-based storage technologies. Fourth, safety standards. Hydrogen handling requires strict adherence to established safety protocols. We reviewed safety codes, best practices, and regulatory frameworks that ensure safe handling and operation throughout the supply chain. Finally, fueling stations. We assessed station design and components, permitting, operating requirements, and compliance with dispensing codes and standards. Next slide, please. This slide outlines key infrastructure-related challenges identified for deploying hydrogen fuel cells technologies at facilities. Cost is a major barrier. Detailed cost information will be discussed in the next slide. Permitting remains complex. A standardized process. Sorry, can you please go one slide back? Yes. Permitting remains complex. A standardized process is still under development at the state level, leading to uncertainty and potential delays. Is this slide, can you please go to slide 44? That's where I was at. All right, sorry about that. So yeah, now we're at the second bullet point, which is permitting. So permitting remains complex. And then the third bullet is timelines for hydrogen infrastructure along, further slowing development. Technical challenges include hydrogen loss during gaseous and liquid storage, and immature technology for material-based hydrogen storage. Safety remains a key concern. Hydrogen requires rigorous safety measures due to its handling characteristics. Maintaining public and workforce confidence is essential for successful deployment. Next slide, please. Now we'll move on to the economic considerations of electric CHE. Equipment capital costs include the purchase of electric CHE, which can be 1 to 2 times more expensive than diesel equipment, onboard batteries, as well as the cost of associated charging equipment. Operating costs include electricity, routine maintenance, and midlife battery replacement. Infrastructure costs over utility-grade infrastructure upgrades, charging stations, as well as infrastructure costs cover utility-grade infrastructure upgrades, charging stations, as well as infrastructure maintenance. Costs vary depending on different locations and types of infrastructure projects. One notable example is that the cost of building a new utility substation can range from $8 million to as much as $30 million, depending on site conditions and power demands. The cost-related information and insights included in the assessment were gathered from OEMs, stakeholders, equipment dealers, and other government agencies in an effort to inform future planning and investment decisions. Next slide, please. Now let's turn to economic considerations for hydrogen fuel cell CHE. Capital costs are high. Normally, fuel cell CHE can cost over twice the price of diesel CHE. Based on available cost information, fuel cell CHE costs approximately 1.2 to 2 times higher than diesel, depending on the equipment type and the manufacturer. Mobile refuelers, if needed, can add to capital costs. Operating costs include hydrogen fuel and fuel cell system maintenance. Most fuel cell CHE include onboard batteries, so battery replacement should also be factored in as operating costs. Infrastructure costs can vary depending on if the hydrogen is produced on-site or off-site. The costs of on-site hydrogen production infrastructure can be different depending on production methods, production capacities, location, and the local regulatory policies. When hydrogen is produced off-site and fueled on-site, costs should account for fueling stations installation, maintenance, and operation. For hydrogen fueling stations, operational costs mainly come from the electricity required for hydrogen storage and dispensing. Next slide, please. With that, I'll pause here and open it up for questions and comments. If you'd like to make a comment or ask a question during the discussion, please use the raise hand feature. You can also submit questions by using the Zoom Q&A box. If you're calling in by phone, press *9 to raise your hand, and we will unmute you when it is your turn to speak. While waiting for questions and comments, we can look at this battery electric storage system as part of a port microgrid at the Port of Long Beach.
So Tiambo, there's a couple in the Q&A if you'd like to start with those.
Yes. All right, the first question is Lauren. Thank you for your question. Regarding the 21 out of 28 facilities that have sufficient power, please quantify how much power is needed by the remaining 7 facilities. Is it 25% of total projected power needed? Since CA largest ports are included in the 7, it seems like it might be much greater than 25% of the needed. Yes, so to answer your first question, so how much more power is needed? It was provided in appendix, in our appendix F. We have detailed information on how much more power was needed for each facility. You can look at appendix F for that information. Is it 25% of total projected power needed? No. I think the remaining 7. So when we talk about 21 out of 28 facilities, we were referring to all the facilities that we analyzed, and these are the numbers of facilities that we analyzed. when it comes to the total projected power needed, we were not referring to, so basically not every facility needs the same amount of power. So the answer to your question, is it 25% of total projected power needed? The answer is no. And since CA largest ports are included in the 7, it seems like it might be much greater than 25% of the need. Yes, it will be. So I think that answered your question. So let me just wrap up. I'm sorry. So basically, for when you mentioned the 75% and 25%, you were only talking about the facilities. However, not every facilities have the same amount of power that's needed in order to support full ZE, because different facilities have different ZE fleet size. Different CHE fleet size. So, and then because 7 of the facilities here include some of the biggest facility ports, such as the Port of Long Beach, Port of Los Angeles, and the Port of Oakland, and those sites, they have a larger CHE fleet size, and then they will also need a higher power need as well. So they will actually be greater than 25% of the need. The next question from Anonymous. Did you speak to the utilities as part of your analysis? The answer is yes. We did speak to utilities during our analysis. And then we gathered information and data, and then through them. Yes. And then among the utilities that we engaged include ACE, LADWP, yes, and then
also the Port of Oakland is their it acts as their own utility management. So we spoke with them as well.
Yeah, we also spoke with PG&E as well, and then ACG&E. So pretty much all the utilities, big utilities here at California. And any more questions? And also, I want to follow up with one of the questions that Lauren, you mentioned with the, it's also related to infrastructure. When you talk about the GFO, the CEC has a GFO on the street that requires 3 CHE to charge at each charging port. So I want to specify that when evaluating infrastructure needs, it is very important to consider site-specific conditions. And currently, it is very unclear that whether assigning 3 units to a single charger is feasible for all facilities. Maybe for some facilities they are feasible, but we're just not so sure about those type of information. And then we do believe that technology will continue to advance, and we will definitely actively monitor and gather updated information on charging capabilities. And also to add on that question, even if charging 3 CHE to a single charger is possible, whether some types of CHE can operate 2 full shifts without recharging at all still remains uncertain too. We know that some OEMs, they were able to meet this performance level, but we're not sure about if this is consistent across all manufacturers. So it is still currently a challenge for even just a 2-shift operation itself. Yeah, hope that answered your question, and then thank you for your question.
Looks like that's it for now.
All right. With that, we can go to the next slide, and Jeff will.
Okay. Thanks, Tiambo. Each technology section in the assessment has a table describing the technology outlook for each type of CHE to achieve equivalence by 2035. This summary table is a summary of the outlook for all 75 CHE technology combinations to achieve the technology readiness grade of equivalence by 2035. I'll walk through some of the highlights, starting with the first row below the header. We can see that there are 3 types of CHE that achieve a technology readiness grade of equivalence already. These 3 are battery electric AGVs, grid electric rail-mounted gantry cranes, and grid electric ship-to-shore cranes. The next row down that starts with likely shows that there are 2 battery electric CHE that will achieve technology readiness grades, a technology readiness grade of equivalence given current regulations and incentive programs. These are battery electric forklifts and yard trucks. The next row that starts with only shows that most types of battery electric CHE can only achieve equivalence with additional emissions reduction strategies and incentive programs in place. The next row down that starts with dependent shows that there are many types of battery electric and hydrogen fuel cell CHE that are dependent on other CHE with similar zero emission fuels to achieve equivalence. These are mostly facility support CHE because it is likely that facilities won't invest in the infrastructure to convert this CHE to zero emission, since it generally isn't used to move cargo. As an example, if a facility invests infrastructure and charging stations for battery electric yard trucks, they may be more inclined to purchase battery electric railcar movers or aerial lifts. The same holds true for hydrogen fuel infrastructure. The next row, starting with not likely, indicates that there are several types of CHE which passed the technology applicability screening, but will not likely be able to fully develop and test the equipment sufficiently to achieve equivalence by 2035. Most of the CHE that fall into this category are hydrogen fuel cell CHE. The last row of data shows the 20 CHE technology combinations that received a technology applicability score of 0. Next slide, please. In conclusion, a lot of progress has been made to transition to zero-emission CHE. For example, of the 25 types of CHE that were evaluated in the assessment, 24 types have a zero-emission, commercially available model. 23 of these are available in the US. 3 types of zero-emission CHE achieve a technology readiness grade of equivalence. And in California, 100% of these 3 types of equipment are zero emission, representing over 400 pieces of zero emission equipment. 2 types of CHE will likely achieve equivalence within 10 years, given the current regulatory and incentive program environment. The image on this slide is the hydrogen fuel cell RTG at the Port of Los Angeles that we were able to see during our visit there. It was very cool to see that in action. Next slide, please. Although much progress has been made in the development and adoption of zero-emission CHE, there are still many challenges. Most of the CHE evaluated do not achieve equivalence, and most likely will not achieve it within 10 years without market interventions such as additional emissions reduction strategies or incentive programs. This is based on the technology readiness grades of the CHE, the lack of available infrastructure, and the generally higher cost of zero-emission CHE compared to diesel models. Infrastructure challenges, high costs, and equipment reliability must be addressed for widespread adoption of zero-emission CHE. While there is a zero-emission solution available for almost every type of CHE, a significant amount of public and private infrastructure is needed to deploy these CHE. Grants, clean air programs, and financial incentives are needed to help fund both the equipment and the infrastructure. The picture on this slide is the newly opened hydrogen fuel cell truck refueling station at the Port of Oakland. While not specifically for CHE at this time, it shows the progress being made with infrastructure development to support clean air around our seaports. Next slide, please. The assessment has a lot of good information, but there wasn't enough room for everything in the body of the document. So we also have 9 appendices that we have listed here. and are referred to throughout the assessment. I'll give you a moment to read through these and jot down any questions you may have about the appendices. Next slide, please. Okay, we're almost done. There are just a few more items that we'd like to cover before opening up for questions and comments. Next slide, please. There are several requests for additional information throughout the assessment. The requests are put into boxes like the example shown at the bottom of this slide. In general, we would like the following information for all 3 zero-emission technologies. Feedback for any zero-emission CHE implementations, including outcomes, challenges, repairs, lead times, and timelines. Equipment cost information, including capital expenditure, fuel, electricity, maintenance, or operational costs. Infrastructure information, including power source solutions, project cost, permitting challenges, permitting costs, and best practices. And any zero-emission CHE or demonstration projects that are not listed in our appendices. Next slide, please. We want your input. If you have any comments, feedback, or supporting data, please send it to our CHE mailbox at cargohandling@arb.ca.gov by December 12th. This year, 2025. After reviewing all feedback and making any necessary changes, we expect to finalize the assessment by mid-2026. Next slide, please. Here's the link to our website where you can find today's slides and the technology assessment. If you haven't already, I encourage you to subscribe to the Cargo Handling Equipment email list. This is the best way to stay informed about future meetings, updates to this assessment, and CHE-related activities. We've dropped the links in the chat for easy access. Thanks again for your attendance today. And with that, I'll turn it over to Joelle to open it up for general questions and comments. Next slide, please.
Okay, it's our final Q&A session. Let's open it up regarding any of the topics we've talked about here today. While we take questions, we'll look at the battery electric loader that was displayed at the Advanced Clean Technology Expo in Anaheim this year. Remember to ask a question if you're joining on Zoom, raise your hand if you want to speak. Also, if you want to use the Zoom Q&A box, and if you're calling by phone, press *9 to raise your hand and we'll unmute you. Okay, it looks like there may be a question for Tiambo in the Q&A. Kevin?
Yes, I can take the question from Kevin. Thank you for your question. The question is, does CARB have draft timelines for infrastructure development at the Port of Los Angeles, Port of Long Beach, and the Port of Oakland? These are critical to gauge the time until significant deployment of the battery electric and hydrogen fuel cell can occur. The infrastructure implementation timelines are critical to know to assure adequate stakeholder input and to facilitate private investments in zero-emission vehicles and other technology developments. There may also be additional zero-emission vehicles and near zero-emission vehicle technologies that could be deployed in the interim to gain additional reductions earlier. Thank you for your question, Kevin. We are actively following up with the infrastructure timelines for the 3 biggest ports in California: Los Angeles, Port of Long Beach, and Port of Oakland. And then Port of Los Angeles and Long Beach, they just had their 2024 zero-emission cargo handling equipment feasibility assessment. In that assessment document, they mentioned where they're at with the infrastructure readiness. You can take a look at that document. And then, and also, Port of Los Angeles and Long Beach, they're working on a cooperative agreement with the South Coast AQMD. That agreement was about infrastructure as well. And then we are actively following up on this. So if you need more information, please don't hesitate to reach out to us, and I can follow. I can send you the documents. And then We understand that these are very critical, but because of the current but it also depends, the infrastructure, it depends on a lot of factors, political environment, costs, and then the utilities and the power availability. So it's just going to take, we believe that it's going to take time for infrastructure to implement, and it will still remain uncertain as we build out infrastructure. The best we can do is just to actively work with, actively follow up with facilities and utilities to learn the most up-to-date information on those infrastructure timelines. So that is a really good question. I guess the answer to that is that it is uncertain. We cannot provide a very specific timeline for those type of infrastructure development. But thank you so much for your question. And then the second question from Chengfan1, thank you so much for your question. Could you elaborate what does additional incentive programs mean? Do you mean incentives are in additional to CAR Moyo, CAP, and CORE, and other programs that are currently available? I think Leah can take on this question.
Yes, that is what we're saying. We're saying in addition to what's currently available, more incentive funding will need to be made available for us to meet, or for those equipment types to reach equivalence.
And the next question from Anonymous, will there be a push by CARB to push for zero emission construction equipment to increase the need for production, similar to those seen in Europe and China? I believe that is a question that Leah can take on as well.
So we'll have to look into that offline. CARB does have a number of off-road there's a small off-road engine regulation, there's the in-use off-road regulation, but I'm not quite sure where they're at as far as pushing to zero. And then there's also the federal, or the EPA has the authority, only EPA has the authority to regulate certain construction type equipment. So if you want to follow up with us, and let's see, this is anonymous, right? Yeah, you'll have to follow up with us offline. If you want to send your email to the cargo handling email, we can get back to you on that with a better answer.
And then I believe there's one more question from Anonymous. Could you share additional information about timelines and next steps for the incorporation of the findings of this draft/final tech assessment report into the scoping update /SIP?
I can take that, Tiambo. We appreciate everyone's input today and the good questions and discussion. We are going to assess all of the relevant information that we get during the comment period, which ends just about a month from today, 1 day less than a month. So after we review all of that, we will incorporate what we find relevant and hope to publish the final draft in the middle of next year. I don't know if I answered that completely. Leah, did you have any information you wanted to add to that?
No, I think you did it fine. Like she said, after we finalize the TA, we'll determine next steps. What that looks like, we're not quite sure yet. And if we do proceed with any type of regulatory activity, then that would go into any SIP planning processes. But as of now, no plans to do that.
Okay, last call for questions. Anybody want to ask live, raise your hand, or answer it in the Q&A? I think we should play the Jeopardy theme song. Okay, we have another question. Okay, if the assessment is used for future rulemaking, will the estimated costs listed in the assessment be adjusted upwards based on current economic conditions at the time? I can say if we do undertake a rulemaking, we will definitely be looking at the full costs going forward at the time that we are evaluating. So I hope that answers that question. Rulemaking does take a lengthy amount of time because it's a public process and it's well established. It takes about 3 to 5 years. So we haven't even considered in which direction we want to go forward at this time. So it would be sometime down the road after we finalize this document, and we'll make those choices at the time that we'll evaluate those at the time that we make those choices, if that makes sense.
Yeah, and to add to that, so our current tech assessment, we did not include an industry-wide analysis for cost data. All of the cost data were just gathered from either literature's public report or our engagement with stakeholders or OEMs. And then if we decide to move with a new rule, we will be required to fully assess the costs to industry as part of the regulatory development process.
And
Thanks,
as we all know, a lot of changes happened after January 2025 with respect to industry costs and so forth. So yeah, we're definitely aware that a lot has happened since our cutoff time. And so yeah, if as we move forward, if we head that direction, we'll have to reevaluate.
Thanks, Jeff and Tiambo. We have another question. Will the meeting recording be shared or posted online? It will. I dropped a couple of links into the chat. One is the cargo handling email address, which we would encourage everyone to send us feedback on the technology assessment itself at that email address. And then the draft technology assessment is available at the final link that I put in the chat, and you can access the technology assessment, and the recording will be posted at that same address. Also, the many appendices are available at that location as well. Anything else? Any further questions? Okay, well, we appreciate everyone's attendance today. We thank you for joining us. Again, we just ask for your assistance with feedback, anything that you think that we should include, definitely alert us and we will be aware. Thank you for joining us today.